Hi, this is Krisha Cepeda with the Sanborn Map Company, and today I'll be speaking about generating a three-dimensional model in a geospatial system, and then using that geospatial model as in creating a digital twin. A little bit about Sanborn. We are the oldest continuously operating mapping company in the U.S. We've been around since 1866, yes. We actually started out being high accuracy surveyed fire insurance maps, and a lot of environmental company and other types of companies still use those maps today. They're very, very accurate. And you can actually convert them into your GIS, and it's amazing how well they hook up. But now we're, modern 21st century company. We have had a lot of firsts in the industry. We continue to lead the technology, pioneering orthoimagery in '88, going to imagery sensors in 2004. Now, prior to that, we used to have negatives, film negatives in the camera, which were like 9" by 9". And of course, everything's digital now. We've always been kind of on the leading edge. So we do the full gamut of geospatial products and services, including visualization systems, which I'll be talking a little bit about today, cloud services and whatnot. But the bulk of our work, this pyramid kind of shows the percent of the work that we do in each one of these components. Our data map production, which includes LiDAR, oblique imagery, orthos, contours, and whatnot, actually still makes up about 85% of the work we do. So we feel the GIS value chain really starts with high accuracy, intelligent data. So it's critical that your base map be continuously updated, accurate, and intelligent. So today I'm going to talk about creating a digital 3D model, different levels of detail of the modeling, then taking that 3D model and being able to enhance it so to develop a digital twin and end up with a couple of applications. So we base our modeling on what they call a city GML. It's actually an enhanced version of levels of detail. And there's a levels of detail 0 through 4. They start out with the simple footprint, and then that get more detailed as you move into number 4. So here you have a screenshot of the different levels. LOD 0 is your simple footprint. A lot of you have this in your existing geospatial GIS system. The next level of detail up is number 1. And what we do is we'll take the elevation of the building, we'll extrude it down to the ground footprint and create what we call a sugar cube. The next level is a level 2, which starts to come into other architectural details such as domes, slanted roofs, and whatnot, as you see here. Level 3 gets into much more detail. We add in all the different appurtenances such as stairways and chimneys and air conditioning units, patios, and whatnot. Level of detail 4 gets into internal building modeling. So each one of these levels, you can have just no texture at all, or you can put realistic imagery on the sides and tops, or you can provide a computer generated. So I have a couple of samples real quick here. Here's your level 0. Again, your footprint, very simple. Here's the level of detail 1, where you can see you've got a lot of information. You have all your buildings, how they're related to each other, and basically the mass and general minimum bounding polygon for each of these buildings. But you don't have a lot of detail on top of the buildings. You don't have appurtenances and things like that. But it is a good stage to start out with. This particular sample, again, has no texture. Here we come into the next level where you start to add more appurtenances, such you get your air conditioning units, you have windows on top of the building, just a lot more details on the different levels and shapes of the building. And this particular one is computer generated texture. Similar type model, the level 3, is shown here with the realistic texture. And this texture comes from ortho imagery for the rooftops and oblique imagery to texture the sides of the buildings. Your fourth level of detail goes into the interior of the building, and this is becoming more and more popular. Now that we've got a handle on our exterior environment, we need to also get a handle on our interior environment. So there is various sources for this. You know, you could have old CAD building plans, as-built, blueprints, things like that. But also you can, it's more and more popular now. There's a lot of sensors out there that you could take inside a building and collect LiDAR and imagery. And as a matter of fact, we have developed an indoor mapping autonomous robot that actually moves through the building on an automated basis and collects LiDAR and imagery. This happens to be the San Pedro's baseball team in San Diego. We took our little robot in there during one of the Esri conferences. So now you have a 3D model that you can start to base your digital twin on. And I'll do a little, in my next slide, I'll talk a little bit about what a digital twin is, but basically your 3D model is really like the first phase. It's an excellent basis for you to start to develop your twin. But it really requires more enhancing with additional features and attribution, and it needs to connect to the real world. So I have a description, next slide, on what really is a digital twin. It's a realistic representation of a physical product, entity, or your city. And I think us GIS users are really applicable for building smart cities in digital twins. Because the digital twin really started out in the engineering environment, but now we see the power of it for building smart cities. So it does require, one of the things it does require is connection to the real world. It has to have Wi-Fi or video, live sensors spooling in from a pole on a sensor on a pole or something like that. And basically it's combining all these assets of your city and all their attributes and put it together in one model system that's connected to the real world and all in one place. And actually NASA first used this technology for space exploration. So the concept goes back almost 20 years. So why do you have a digital twin? Well, it just allows you to test and model the digital world instead of the real world. It's more efficient. Again, it started out really with like engineering, so they could do digital prototyping rather than physical prototyping, which is incredibly more efficient and gives them operational efficiency. Now it's enabling us to build smart cities. So we could have simulation and scenario planning. We could design, maintain, optimize the way our cities work, controlling and analyzing the environment and everything within it. So we have the 3D model. Now I'm going to talk a little bit about adding the content to the 3D model to continue to develop this digital twin, now that we've gone through the explanation of what a twin is. So typically, a lot of source data would come from imagery or LiDAR, either aerial or terrestrial. Oblique imagery for putting into your 3D model and digital twin is much more valuable than only having the single nadir sensor that's been around for years. You know, your ortho imagery comes from the nadir, NADIR sensor, which is your downward looking sensor from the camera. But oblique imagery gives you 4 more views and a lot more information. For instance, in a city, you could start to see important assets that you want to put into your digital twin, set signs. You know, what type of sign is this? What does it say? You know, what this is looks like a, you know, a trio of traffic lights. This is a single one. All this information and all these different assets now that you can start putting into your digital twin to connect with the real world with sensors. So feature extraction from the imagery is a typical way to get information into your digital twin. We have automated processes that will do vector mapping, or what could be done manually. There's a lot of different types of processes that can be used, but basically it can start to, you know, digitize your road network, your buildings, and just build and build and build upon your twin. And so you can use this information combined even with some ground truthing and guess, do prediction and simulation and that type of analysis. LiDAR, we can also get information from. You know, LiDAR is becoming more and more and more critical for extracting features. It's the more denser the LiDAR is, the more features that we can extract out of it. You know, you could basically direct georeference, you know, billions of points from your system. You know, classifying vegetation instructions as structures is very common right now when you collect your LiDAR and you're doing your point classification. But we're also definitely been expanding into extraction utility features, especially for utility companies and whatnot. And everything can be extracted in 3D. This is another example of extracting features from LiDAR. This happens to be a mobile LiDAR project that we did, where we were able to extract the utility lines and whatnot. So we took the LiDAR, extracted the features out of it, and built a CAD model. So one of the other things you need to do that's important is to keep your digital twin up to date. So in order to do that, you know, use similar technologies of either imagery or LiDAR or both. You know, you can edit the digital surface model. You know, digital elevation model is basically your bare earth that's used to create your contours and whatnot. Your digital surface model is everything else. It's basically your 3D model. So it includes all your buildings and all your vegetation and whatnot. So that can be edited with new LiDAR imagery. We can edit texture by bringing in new imagery. You know, use the imagery or the LiDAR to remove, edit objects. You can have changes, deletions, and new features into your twin. This is an example of a digital twin that we built for the country of Qatar. It was almost 1,000 square mile area for their utility and pipelines. And we literally digitized like hundreds of thousands of assets. And they have different sensors that now feed into their digital twin where they can analyze, which assets need to be maintained, how old they are, what they look like, and get all that informational feed from their digital twin. You know, law enforcement also in a smart city, you start bringing in your 3D model, where this was an example of a VIP coming into the city of Denver, Colorado, developing a threat dome of where the primary meeting would be, and then bringing in different simulations of point of site analysis, where there could be, shooters on different rooftops, things like that. When real live interaction with the cars as they're driving in. So they use it for planning. And then when the event is actually going on, you use it in real time. Again, you could have sensors on the tops of these buildings looking out for nefarious people and keeping track of everything that's going on during the event. Again, smart cities bringing us lots of information. So autonomous driving, this is up and coming. I'm hoping my next car will be autonomous. I think the first phase will at least be that they'll drive on the highways and then eventually get into the, the more suburban and rural areas. But, in addition to having sensors and whatnot on the car, you really need to provide a digital twin of your road networks and your signs and sidewalks, and have real-time video feeds of what's going on for traffic, and especially in areas of construction and whatnot. So you're building your basic twin and then incorporating it with the autonomous vehicles. Have a lot of intelligence embedded in there. And again, connecting by being connected to the real world. It's the only way that this is going to happen, is really like approaching like an artificial intelligence. So applications, I think I've gone through a number of these. What I see for our geospatial environment and GIS users is really the essential tool for having smart cities. Being able to do urban planning and land use and transportation, tracking weather, utilities, your pipes, your, what type of pipe you have, how old it is, being able to have sensors that determine the health of that, when it has to be maintained, when it has to be replaced and whatnot. If you have large facility buildings where you could map, every floor, every stair, analyzing and controlling your elevators. You can even monitor your location of people, how many people are in certain offices and how they move about and whatnot. And even, document management, having a place to store your as-builts and your service history and maintenance and all that type of thing. Again, I think that's the critical use for us GIS users. Engineering, they consider it part of the product lifecycle management, which starts from the very start of design phase. Again, they don't have to do multiple prototypes of different designs for a certain component. They could do the whole design planning and whatnot down into like the producing the final product digitally before determining that, hey, this is going to work, there's no issues, and they can be successful in that and much, much, much more efficient. So it makes us smart and it makes us efficient. And then again, the autonomous vehicle driving, which is critical for. I can't wait to get an autonomous vehicle, especially once this virus is gone and we start traveling again. So that's it. Thanks for listening. If anybody has any additional questions now, let me know in the chat room, or don't hesitate to email me, call me. I'd love to talk to you, and so glad you could join us today. I know it's difficult in a virtual conference, and I'm sure we're all looking forward to getting back into the real world. But for now, we're going on as best we can. Take care.
Tricia?
Yes.
There are 2 questions in the chat.
Okay.
Connie would like to know, what could the final digital twin deliverables be? and in what format?
It could be provided like in an ARC portal that you can access the digital twin through. That would probably be for most people that use the Esri environment. We would provide that in an ARC portal for you.
Okay, and then we have two more questions, so I'm just going to read them to you. Brian Burrell asked, have you run or have any images of flood or hydraulic modeling in combination with these 3D models?
We do build a lot of hydrologic models. You know, part of our LiDAR production, most of our LiDAR products that we do for the USGS and other agencies include digitizing the water bodies and streams and whatnot, usually like water bodies like an acre or larger, and streams like greater than 50 feet wide. We then incorporate that into the LiDAR model, and we we flatten and enhance that LiDAR model with the water, and then from there you can go on to doing different types of hydrologic modeling. We also, what they call, when we're building this water model, we make sure it has monotonicity, which means that everything flows downhill in the way it should. Because, you know, let's face it, LiDAR, you know, you're accurate to 6 inches plus or minus typically, but things are kind of, you know, jumping, they're a little bit under, they're a little bit over. So we ensure that everything comes down into that like average flow, and that it all goes downhill. So that's typical in what you would see in like creating contours and whatnot. So your contours, as you come down a stream, you know, they point up and down like they should in the direction of flow. We have another phase where you further hold the model to completely be joined into, let me explain it. Typically, if you think of a contour model, if you have a culvert going under a road, you don't cut out the road, you leave the road in there and your contours go down along the sides of the road. In the enhanced model, you actually cut out that culvert from the LiDAR model and the water flows through it. So you get into this like fully water model that flows throughout your whole city or county. Hopefully that makes sense. So the first phase is hydro flattening and creating a contour type model where you remove things like a large bridge, but you wouldn't remove a culvert. And then you have the enforcement of the model where you're digging out your culverts. And then if you can also see where water might come out of the ground, go in and out of the ground, and you're linking up that whole water system model. And you use that for lots and lots of, you know, FEMA flood modeling and whatnot. And hopefully that answers the question.
All right, we have two more that came in. Sam Feldestein would like to know, would this somehow be able to be used in Esri's roads and highways?
Yes. I would definitely say yes.
Okay, and then Ryan Arthur says, I'm interested in the life cycle for transportation projects, particularly going from design to construction and verifying what was built and how you go from CAD to GIS back to CAD. Reason for the GIS in between could be doing field verification after construction. Not sure if that is typical process, however.
Well, we are more of a mapping company. We're not an engineering company. So we provide a lot of the data in order to let the engineers build things. So, or maintain things. You know, if they want to do say they want to do a new they want to design their transportation network, or they want to design new bridges. We collect all that information for them, and then they take that information and they'll build their designs and whatnot from it. However, what we also provide them a CAD type model. So we don't just give them the imagery or give them the LiDAR. We'll give them we'll build actually vector line work inside a CAD environment. Everything is, in a realistic coordinate system so that they can work inside that. So kind of like I showed a little bit of this instance where we took the LiDAR, the mobile LiDAR. So here you have the LiDAR, which is basically you have your points, and your points are classified in that originally. We then extract out what we call, this is vector line work. You have your roads, you have your utility lines and whatnot, and then we convert this into the CAD environment. And then the engineers can use this to manipulate, do new designing and whatnot. If they say they want to manipulate, they want to change this intersection, they want to have an overpass, or they want to add turn lanes or anything like that. So we're providing them that CAD environment to work in where they can do their design. So we're not the actual engineers, but we provide everything to the engineers in whatever format they like. A lot of engineers they really don't use GIS. They want a CAD environment like this inside AutoCAD or something like that. So we provide just a variety of different formats. Again, the GIS is typically would be like in, ESI shape files or things like that. But when it comes to engineering design, the engineers and whatnot, they really want the CAD type drawings. And I hope that answered that question.
Great. That is all the questions that were in the session chat.
Wow, we're like exactly on time. Thanks to everybody who attended. I really appreciate your participation. And again, please don't hesitate to contact me or anyone at Sanborn. If you go on Sanborn, www.sanborn.com, you can find my point of contact information there. And there's also an 800 number. So if you need any more additional information, please give us a call. And take care and enjoy the rest of the conference.